All right. Where we left off in class, I think with all three of my bells, is we left off talking about multiplicity. And just to kind of remember, multiplicity is the number of times the factor occurs. And if you have an even, it's going to be tangent to, which we said touches or bounces. And if it crosses, that meant that factor was used once or 3 or 5 or an odd number of times. So that's where we left off. What I suggest you do is try examples 2 and 3, pause the video, try 2 and 3, and then I'm going to kind of walk through those answers now. So on example 2, it's asking how does the graph behave with the relation at x equals 2. Well, if we look at this function, which is in what we call factored form, because you can literally see each factor, this has a multiplicity of 2. So we said that when it's even, it's going to be tangent to. So if you look at my sketch over here, which you probably did at the very end, if I go to x equals 2, which would be the solution when you set this equal to 0, you'll notice that my graph is bouncing or tangent to the x-axis. The real zeros, well, if you were to set this equal to 0, when will this factor equal 0? -1. This would be at 2 and +1. So these are the real zeros for sure. Now the degree is 6. So we have 1, 2, 3, 4, 5, 6 for our exponents. So that means we're going to have 6 solutions. 3 of them are real. So they're either going to have to be repeated, which we know one of them will, and that means we possibly are going to have some imaginary solutions. But right now we're not going to worry about that. And then I think everyone did really good with in behavior. Because the leading coefficient is negative and we have an even degree, both ends of the graph are going to go down. So as x approaches infinity, the y values, f of x, approaches infinity. As x approaches negative infinity, the y values approach negative infinity. Ooh, I'm glad I caught that. Okay. So, I need to fix both of these. Wow. All right. Good thing I go over this. Okay. Let's go on. To this one, we're going to be given that the graph is already graphed for us. So what happens is it says the local min and the local max. And we talked about this. That's at your turning points. Okay. So we have these turning points that I'm going to kind of highlight in purple here with points. And what happens is we want to look at these dips. So the 2 dips occur. What you want to do is you want to give the y values. So this y value is at 2, and this turning point occurs when y is 1, 2, 3, -4. So we have -2 and -4. Our local maximums, you want to give the y value, the highest that turning point gets on the y value is 0. Now, it says the minimum degree. Remember, you can find this minimum degree after looking at your turning points. So since there are 4, then that means the degree could be at most 1 more than that. And then as you write out a possible function, for this one, you have to be careful. We have a turning point that bounces. So these are bouncing at -6 and 0. So notice I have a factor in here where x is 0, and here x would be -6. So I need those to have even multiplicity. And then it's crossing at 5. So I want an odd multiplicity. So if you have a 3 here or a 5 here, well, you don't really want 5 because we can't have more than 5 solutions. So that's why if you think about my degree here, 1, 2, 3, 4, 5. So my degree of this factored polynomial is 5, and I'm showing that these have even because they're bouncing, okay? So just be careful when you sketch your own. You just can't do whatever you want. You have to follow the end behavior. For instance, this graph should have a positive leading coefficient. Mine does. It has an odd degree. Mine does. I have 2 tangent to the x-axis, and so I have 2 even multiplicities and 1 odd, okay? So just be really careful that you're following all the things that we've learned so far about your multiplicity, okay? All right, I'm going to walk through the following examples with you and kind of work them out, okay? So a lot of this is going to be really straightforward and fast, but finding the roots means finding the solutions. So I think we're at a level where if you still need to recognize that you have to substitute in 0 for the y value to find your x-intercepts, or what we call roots, please do that. But basically, I know that this whole thing will be 0 if x were -3, x were 2, and x were -1. Now, when you state the multiplicity by each one, you just need to look at your degree. So this has 1 factor, that is x plus 3. This has 1, and this has 1. So if we go on and we use that 0 product property, I would have x equals -7 and x equals 3. This has a multiplicity of 2, and this has a multiplicity of 3. And remember, that multiplicity is telling you how many times that factor or solution occurs, and it's telling you whether the graph is going to be tangent to the x-axis or odd crosses the x-axis, okay? Now, on this one, we're going to have to look at this and say, okay, we're going to need to factor this. So we're always going to look for a GCF first. So I'm going to factor out that GCF. And then I'm looking for 2 numbers that give me a product of -20 and a sum of -1. And that's going to be -5 and +4. The difference, and then you need to know this, especially this was on your assignment that was due earlier, is that this is called standard form of a polynomial equation, and this right here is called factored form. And you're going to need to work in both ways, going from standard to factored. If I then multiply this back, I'll get back to where I started to standard. The solutions, or the x-intercepts, are 0, 5, and -4. We have a multiplicity of 2, a multiplicity of 1, and a multiplicity of 1. So you might want to try this one on your own before I kind of do it for us. But once again, we need to factor this so I can look at those multiplicities and individual factors. So I'm going to, since there's no GCF and there's 4 terms, I'm going to factor by grouping. So I think you're hopefully pretty confident with those factoring skills. So since they both have a factor that is alike, that's a GCF, okay. Now, just because you factor once doesn't mean you're done. Right here, I am left with a difference of squares. So I need to factor this completely. That's a 5. So we have the quantity of x minus 4 times the quantity of x plus 5 times the quantity of x minus 5. So we have 4, -5, and 5, and they all have a multiplicity of 1. And really that takes a lot of the things we've done with factoring and solving for x into account, okay? All right, let's go on. The last parts are similar, but they're just going to be working backwards. So basically, at the top, you are going to find a polynomial with the given zeros with the multiplicity. So we know that when the zero product property, we need to come up with where x is 0. So that's x, and then I'm going to square it because we need a multiplicity of 2. I need a solution or an x-intercept of -3, so I want that factor to be x plus 3 with a multiplicity of 1. So when I write that equation, this would be in factored form, or I can write that, and I'm just going to distribute this to get standard form. Now, in your homework, I might ask for both factored form and standard, okay? For number 9, I'm looking at factors. They all have a multiplicity of 1, so they're all going to have a degree 1 on their factor. So that's an x minus 8, an x minus 2, and an x plus 4. Now, I'm not going to do this in your notes, but this right here is factored form. So I'm going to get this started and you'll need to finish this. But to put this in standard form, you're going to need to multiply and get x squared minus 2x minus 8x plus 16. So when I combine like terms, I get this. Now you're going to need to multiply that by x plus 4. So I'm not going to do this for you because this is major junior high Algebra 1 review, but now you're going to distribute so that you can get it in standard form, okay? All right, down to the last 3 kind of examples. You're going to find a polynomial with the degree n with the given zeros. So this first one, if I know I need an equation that has an x-intercept at 9, I'm going to want x minus 9, and then I literally can just cube it. So that one's done. Okay, we're finished. With number 11, your answers could vary here, so I don't want you to panic if they're not like mine, but I'm going to do x minus 4 times the quantity of x plus 2 times the quantity of x minus 5 first to make sure I have all the solutions and what would give me those solutions with our factors. Now I need degree 5. So I'm going to square this one. I'll leave this one degree 1 and I'll square this one. So if you want to put the square here and the degree 1 here, that's fine. Okay? And then finally, if I have x would give me the 0 for the 0 product property times x minus radical 2 times x plus radical 2. Now, you do not want to leave radicals or imaginary numbers in your answer unless you absolutely have to, which you're not, because then that really, we would not have a polynomial if it had an imaginary in it. You can get imaginary answers, but not in the polynomial. And here we want to FOIL this. Now I'm going to multiply this first. So I'm going to, actually let me go back up here first and make sure I have degree 4. So I'm going to square this one. I think that makes it easier to get degree 4. So therefore I have 2, 3, 4. Okay, I was ahead of myself. Now when I FOIL this, I'm going to get x squared. I'm going to get plus radical 2x minus radical 2x minus 2. So what happens is I have x squared from my original times x squared, those cancel, minus 2. So this would be the factored form, or in standard form, I would get x to the 4th minus 2x squared. Okay? All right, I'm going to pause this so that you can do example 13 and then you can check. All right, I'm hoping that you factored out the GCF and then factored so that you could see that your roots are 0, -2, and 2 with the correct multiplicity. The y-intercept I know you can handle, and then all